Hi, so in this video, I'm going to be deriving the differential equations for the concentration and liquid level in a tank with a variable volume, constant cross-section, perfectly stirred tank with time-varying inlet flow and concentration. So I have our tank here. It has a stir because this is a well-stirred tank. We have the outlet hole here, and we have our Q in and our concentration going in, and we also need to find our height, which is the level of liquid that we're trying to find. So to start this problem, we're going to do an overall mass balance. So to start with this, let's go ahead and just start with, we'll have D, and then for now, we're just going to put mass. And this can represent the overall mass of our system. And then this will be over dt. And then basically, we're going to set this equal to, it's going to be equal to the mass flow rate going into our system minus the mass flow rate going out of our system. So for that, we'll have our rho in, our density going in, multiplied by our Q in, minus our density out, rho out, multiplied by our Q out, Q out. Now, the mass of our system can be rewritten as the density multiplied by our height of our liquid multiplied by the cross-sectional area. So if we rewrite that, instead of having mass, we'll have D times rho, our density, and this is the density of our system, so let's put S multiplied by the height multiplied by our cross-sectional area, which is AC. This is all over dt. And then, again, this will be equal to our rho in multiplied by Q in, subtracting our rho out multiplied by our Q out. Now, in this case, we are assuming that A does not alter the density in any way. So in that case, our density going in and density going out will be the same. So then we can cancel those out. Also, we can pull out our cross-sectional area because that is a constant. So if we do that, we're just going to be left with AC multiplied by DH over DT, and then that's just going to be equal to our Q in minus our Q out. Okay, so now we're going to need to apply Bernoulli's equation, and what we're going to apply this to specifically is two different points. We're going to have a frictional point that is located on the surface of our liquid, and then a point that is located at the outlet in which the liquid is leaving. So let's write out Bernoulli's equation to start. So for that, we'll have P2 minus P1 over rho plus V2 2 squared minus V1 squared all over 2 plus G multiplied by Z2 minus Z1, and we're going to set that equal to 0. So taking a look at this, we have our pressures here. Now, the contents of this tank are open to the air, so we're going to assume that both of our pressures are atmospheric pressure, so therefore those are going to cancel out. So we can cross that out. And then also taking a look at our V1, we can assume that, V1 is small enough that we can just go ahead and say that it's 0. So we can cross that out. And then looking at our potential energies, Z1 is going to have more potential energy than Z2. So because of that, that's going to end up giving us a negative GH. So for this, we want to solve for our V2. After simplifying this, we're going to be left with that our V2 is equal to the square root of 2G multiplied by H raised to the 1/2. Okay, now next, the velocity of the flow rate going out multiplied by the cross-sectional area of that outlet hole will give us the volumetric flow rate going out, which we do need. So for that, we can have that our Q out is going to be equal to the cross-sectional area. So let's put A, and then we're just going to put hole because this one is for the outlet of our tank. HOL. And then we're going to multiply that by what we just solved for. So the square root of 2G multiplied by H raised to the 1/2. Okay, so now that we've solved for that, we can actually go back and place that substitution in, and also because we pulled that cross-sectional area out because it was a constant, we can divide that over to the other side. So if we do that, we'll be left with DH over DT is going to be equal to 1 over the cross-sectional area, AC, then multiplied by our QN, minus our what we're substituting in. So A, the cross-sectional area of our hole, so HOLE, multiplied by the square root of 2G multiplied by H raised to the 1/2 in parentheses. Okay, so the next thing that we want to solve for is we want to solve for the concentration of A inside the tank. So in order to do that, we're going to do another mass balance, but this mass balance is going to be in terms of A. So to do that, we're going to need our cross-sectional area multiplied by the concentration of A multiplied by our height. Now, writing this out, again, that cross-sectional area is a constant, so we can leave that out. So we'll start with AC, and then that'll be multiplied by D multiplied by CA multiplied by h all over dt. And then we're going to have that equal to the concentration of A going in, which is CA in, multiplied by our Q in. Q in. Then we're going to subtract the concentration of A. And the reason we can do this is because that this system is stated to be well stirred. We can assume that the concentration of A inside the tank is going to be equal to the concentration of A leaving the tank. So instead of having Ca out, we can just leave it as Ca. Then we're going to multiply this by the cross-sectional area of our hole. So A whole multiplied by the square root of 2g h to the 1/2. Okay, so now what we can do with this is we pulled this cross-sectional area out so we can divide that over, and then also we're going to need to apply the product rule. So if we do that, then we're going to separate these out, so we're left with CA multiplied by DH over DT plus H multiplied by DCA over dt, and then we're going to have that equal to the concentration of A going in, CA in, multiplied by our Q in, minus the concentration of A times the cross-sectional area of our hole, A whole, multiplied by the square root of 2g times h to the 1/2 in parentheses. And then this is all going to be over the cross-sectional area, AC. Now, taking a look at this, we've already solved for our dH dt, so we can actually plug that substitution in. And now if we do that, and also we're going to divide our H over as well, and our CA, we'll have DCA, concentration of A, over DT, and then that's going to be equal to 1 over H multiplied by, giant parentheses, CA in, multiplied by our Q in, minus our concentration of A, C, A, multiplied by our cross-sectional area of our hole, A, multiplied by the square root of 2g h to the 1/2. And then this will be still all over our AC. And then we're going to subtract CA over AC multiplied by our Q in minus the cross-sectional area of our hole, A whole, multiplied by the square root of 2G multiplied by H to the 1/2.